Hi guys, and welcome to this, my Year 12 Specialist Maths Introduction to Vectors lesson for mathsguru.com. Really good to see you. My name's Darren. If you haven't found my channel before, then I'm going to try and smash through the Year 12 Specialist Maths course as the year progresses. Now, I'm going to start with vectors because that's what I'm studying with my school. I'm on YouTube, believe it or not. I am on TikTok, I know, weird, and I am on mathsguru.com. If you go over there, I've got the methods course, the general course, and now hopefully going to be building up the specialist course as the year goes past. Sign up for free. Basically, anything you can do to help me out when you're on there would be great, but should have downloadable lesson notes, etc., etc., etc. Now, again, I'm not going to insult your intelligence, and in fact, looking at this, part of my screen is actually covered up, but pretty much by the end of this particular video, that is what we are going to cover. Now, I am really grateful to Cambridge because they've given me all our permission to use all of their worked examples. So I'll be mapping my course against there. A lot of people say, well, why do you use Cambridge? Why not the other textbooks? There are brilliant textbooks out there. And actually, believe it or not, cheekily, I tend to go through all the other textbooks and look at their examples and what have you. But I have to say, Cambridge, in my view, have some of the best examples. Now, if you're not following along with Cambridge, it shouldn't actually matter because the theory is the same. Now, I know that you've probably done a bit of vectors last year. You may have had holiday homework where you've been set and do this already. That's fine. I'm just going to try and go through what I think are the important parts about vectors that'll scaffold. And hopefully I'll give you hints and tips of what will be useful as we get towards the VCAA exam at the end of the year. Now, what I want to say to you is actually the VCAA exam at the end of the year is not as hard as people think. It's challenging, don't get me wrong. Your SACs will probably be far harder. VCAA use language, and you've got to understand the language. And I say to my students that I've got at the moment, answer as many questions as you can. Be it from the checkpoints book, the textbook, the VCAA exams, or other resources, because the more you get used to the language, the more you'll realize that there's not really too much that actually is asked, and it is very repetitive in many years, the type of questions that they ask, right? So it should be pretty easy to get a minimum of a 25 just with sort of answering those questions. So what is a vector? A vector basically has sort of a quantity which has a direction and a magnitude, all right? It's got to have a size and a direction. And basically there are examples here, lines having exactly the same length and pointing in exactly the same direction are said to be equivalent. So they are equivalent. This here isn't the same vector, but actually, well, sort of, it is because I just took that arrow and rotated it through 180 degrees. So it has the same magnitude, but it would have a different direction. Whenever we do these questions, I'm going to ask you to make sure that every time you do a SPECS question, think about it geometrically. Can you draw a diagram? Because I know for a fact the SPECS exam, if you can sketch things, use your calculator to draw the graphs, use the functionality on your calculator, it really does become a lot easier. All right, lines with arrows are called directed line segments. A lot of this you should already know. All right, notation is incredibly important. All right, you must make sure that when you do the notation in your exam, you make it correct. Those arrows above the lines, put them on there. Make sure the order of the letters is really important. So here we have our vector A to B, yeah? So basically, I'm just drawing a line from starting at A and heading out to this point B. It's the direction is shown with my arrow, all right? All of these are exactly the same vector, right? They're just called different things, right? They're all the same magnitude and all pointing in the same direction. Now in maths, because notation's a pain in the butt, to be perfectly honest with you, we can write them in all sorts of different ways. And of course, in this situation, we can use something called a column vector, where this is my horizontal movement and this one here is my vertical movement. So, you know, that's saying 3 units along and 2 units up. Later on, when we get to sort of I, J, and K notation, we could also write that AB is equal to 3I plus 2j. Now, in this situation, what's important to notice is that there is no reference to here to where that vector starts, right? That vector can literally be anywhere on a set of axes. It just, all I know is that whatever point I start at, its endpoint is 3 across and 2 up, right? And again, likewise here, 3 across and 2 up. For the moment, we're going to think of vectors in terms of a Cartesian plane. Now, we can also use different letters. So in this situation, I might use the letter V, for example, for a vector. Now, it's great. The textbooks, these slides you can see behind me, which are all downloadable from mathsguru.com, I can do bold. You can't do bold, can you? So you would be expected to do a V and a little line underneath it, right? If you don't do that, you run the risk of losing marks in your SAC, in the exam. Who knows what the examiners will and will not expect, but always make sure you get used to the right notation now. Don't stuff it up now, yeah? Right, size or magnitude of a vector. You are going to see, as this course progresses, that modular sign, those two lines either side, over and over and over and over again. Understanding what it means to be the modulus is critically important. Why? Because you're going to use it, and not just with numbers. You're going to use it with letters and all sorts of stuff. So if I'm wanting to find if that is, for example, AB, then the size of that is going to be the mod of AB, right? So how do we find the size of that? Well, if I know that AB is the column vector 3, 2, then I know that that's 3 across and 2 up. Hold on, it's just Pythag, isn't it? 100%, yeah, it's Pythag. So all I need to do is do 3 squared plus 2 squared and square root it. So in which case the mod of AB would be equal to 3 squared plus 2 squared square root, which is equal to 9 plus 4, or root 13. Now, if you are thinking that I am absolutely condescending at the moment, or I don't know, I'm not trying to be. There are many people out there who will be watching this video who won't have met this before. Hopefully this is useful, all right? The mod of AB. Later on, in another topic in this course, you'll be looking at finding modulus of, let's say, A squared. That's really, really important later on. And in that situation, all you would be doing is actually getting rid of our square root sign. And you're going to say, huh? Trust me, it's all coming up. Now, adding vectors. I think of vectors as one-way street. So if I've got two vectors, let's call them u and v. Here is u and here is v. When you add vectors together, you basically join them. So they're like one-way streets. So here, if I was looking at the vector u plus v, I'm basically putting my u vector and my v vector. Now when I add it, it's like saying, well, how can I go basically from the start of AB to the end of BC straight away, or in that situation, A to C. So A to C would be equal to AB plus BC. And again, notationally this is important because later on when we get to sort of vector algebra and vector geometric proofs, the fact that this starts with A and that starts with A is no coincidence. That ends in C, the whole expression at the end ends in C. So important to get these the right way around. But hold on a moment, I can actually draw this diagram in a different way, can't I? Because I could have done B first, or BC first, or I could have done V first, and then I could have done U. And I would have got that, oh, but hold on a moment, that would have given me exactly the same journey. If I'd actually done here to here, I'm still going to get to exactly the same start point. So what we know is that actually adding vectors is commutative. I can never say that word, right? We can do them either way. We would get the same result. Now adding vectors is really, really easy. If you've got column vectors, you just add the top numbers together and you add the bottom numbers together. It is really that simple. So if I was going to do u plus v there, then I would end up with 5, 2 plus minus 1, 4, and 5 minus 1 is going to give me 4. 2 plus 4 is going to give me 6. Ka-ching, thank you very much. But again, when you are doing this, try and think what it is you are actually doing. And I think to myself geometrically, I've got this point here. I'm going along 5, and then obviously I'm coming back one place here. So it's got to be 4. At the bottom numbers, I'm going up 2 and then up another 4. I've got to be doing 6. Really, really helpful. And I've said here, I can do it geometrically. Hopefully that's just understood. If we want to change the length of a vector, we obviously want to stretch it. And we use that by a scalar multiplier, all right? So for example, if I wanted a vector that was twice as long as 5, 2, and I know that u was equal to 5, 2, then if I wanted to double it, I would actually write it as 2u, and I'm going to do my notation there as well. And that basically just takes all the numbers inside and makes them twice as long. Now you're going to say, oh my God, why are you telling me this? Because it is so important to understand. If I wanted to reverse the direction of that vector, if I wanted to keep it the same magnitude, for example, and reverse the direction, then in which case I would negate it. So I would have minus u, for example. In that situation, it would be minus 5, minus 2. And again, hopefully geometrically that makes sense. If I've got my vector u that's going 5 across that way and 2 up, and I want to basically reverse it, then I've got to go back 5 and down 2, which is going to give me that vector there. It's going to be exactly the same length, just in the opposite direction. All right, and again, if we look at our notation here, minus AB is equal to BA. When I've got a minus, I swap the order of those letters as well. Oh my goodness. Now, I don't fully understand why on earth we have a line segment with low length. The 0 vector, I imagine, becomes important. I don't know why. If you've got any idea, leave a message below in the comments. If you're watching this on YouTube, send me an email. It will make me a better teacher. But the 0 vector basically means that we start one place, we go on some sort of a journey, and we end up where we started with, right? It has no direction and absolutely no length. And I've seen this actually in a trick question in VCAA before. We can also subtract vectors. Now, by that I mean, if you've got this u vector going that way, and you've got a v vector going that way, and I want to subtract them, then I'm really doing u minus v. Well, we already know that when we negate a vector, it's going to go the opposite direction. So minus v is actually going to be a vector that way, right? So that is going to be minus v. So I could think of this as u plus minus v if I wanted to, which means, as I can do here, I've taken the u and then I have put on the end of it this minus v. I've just connected it here, and so that journey gives me u minus v. So again, try and think of this in slightly different ways. I'm sorry, Cambridge, I love you to bits, and I am so grateful you've allowed me to use your examples. You guys rock, but no. Draw a directed line segment of the vector 3 minus 2. Please, come on. If you're out there thinking, is this going to be in a VCAA exam? I've never yet seen them ask you to draw a vector like this. So 3 minus 2 is going to go 3 to the right and 2 down. So there we go. I've drawn a sketch of that vector. State its magnitude, right? So let's call that vector u then. So the magnitude of u is going to be equal to 3 squared plus minus 2 squared square rooted, which is going to give me 9 plus 4, or root 13, ka-ching, thank you very much. All right, so again, the basics are important. I got stuck there. Polygon of vectors. When I was back in the United Kingdom, we did this for GCSE, all right? So by about the age of 15, we were doing these type of things, all right? So polygon of vectors is a plane figure that is described by a finite number of straight line segments connected to form a closed polygon. Okay, all right. So a polygon of vectors is basically where you put them all together and they join to make a shape. So in this situation, as we can say here, we can use our A, B. So A to B plus B to C can be re-expressed or written as A to C. Here, A to B plus B to C plus C to D plus D to E plus E to F plus F to A is equal to 0, because I've basically started where I've ended up, right? So you're going to use a lot of that in a much later example. Parallel vectors. Woo! Parallel vectors basically have exactly the same direction. Doesn't matter what length they are, all right? They can just have the same direction. But how would we find that direction vector? And again, for later on when we get to vector lines and planes, we're going to need very much to think about direction vectors. So we know that u here is equal to 2, 3. And I know that I've got v is equal to 6, 9. Well, hold on a moment. It seems fairly obvious that to go from 2 to 6 and 3 to 9, I've just multiplied by 3. So in that situation, I know that v is actually equal to 3u, which is 3 lots of 2, 3. And again, just to try and crystallize that, because I'm always thinking geometrically now, because I know what the exam makes you do and how it trips people up left, right, and center. Geometrically, that means that I have got u is 2 across and 3 up. So let's draw that in green. So there we go. There is my vector u. Well, vector v is basically 3 lots of those 2, 3. So if I was going to draw that on a Cartesian plane, I might go, well, I'm going to start here. I go 2 along 3 up, 2 along 3 up, 2 along 3 up. Well, there we go. So there is my vector v. If my diagram was half decent, obviously they'd be looking exactly parallel, but v would just be longer. In fact, 3 times longer. It is important to note algebraically that for 2 non-zero vectors are parallel, when they are parallel, there is some k in the real such that u is equal to k times v. All right? It becomes really useful later on. Position vectors, I said earlier that if I told you that vector u was given by 2, 3, well, basically that doesn't give you any indication of where a vector starts. It's just got some sort of direction. All right? If we want to denote it in terms of some fixed point, and generally speaking it is the origin, we prefix or prefix it with the letter O. So OA, for example, would basically always start, and it would describe a vector that starts from the origin and points to a point A. Massively important later on. Three-dimensional vectors, again, this becomes really important, again, a little bit later on, but just note that when we have three-dimensional vectors, for two-dimensional vectors, we basically have x and then y. When it is three-dimensional, what you'll notice is that x actually comes out of the page. Then it is y, and then it is z. That is the convention and the notation, right? It starts, I don't know about you, but my brain tends to fritz when I get three-dimensional space, but the x comes out of the page. Now, by all means, pause this video in a moment and actually have a look at these. I asked my group to actually just stop and think about these. Think about geometrically if these are actually common sense rules. When I have two vectors, a and b, is it true that a plus b equals b plus a? When I add the vectors, does the order matter? No. We said that a moment ago, right? We said that as an example. What about this? A plus b plus c, is that the same as a plus b plus c? That sounded the same, didn't it? Yes. A plus the 0 vector. Well, if I've got a vector A and I'm not adding on any magnitude or direction, it's got to be A again. If I have a vector and I'm adding on the negative of that vector, what you're really doing is saying I've got a vector of some magnitude and I'm taking away. So think about it. If I was adding that together, I'm starting here and I'm ending up here. Does it make sense it's the 0 vector? I should Coco. And again, some sort of MA plus B is equal to MA plus MB. If I add two vectors together and then multiply it by some sort of a constant, is that the same as taking the two individual vectors and multiplying it by the constant? Again, hopefully yes. Now for something completely different. There is questions on this every single year in the VCAA exam. And on the whole, they are fairly formulaic. You are going to deal with stuff called linearly dependent and linearly independent. I'm going to skip forward and come back to that screen maybe a little bit later on. Linearly dependent vectors are when I can take 2, 3, 4 vectors and by scaling them and adding them together, make the third vector. So let's explain that again. Imagine I've got the vectors u, v, and w, all right? So here is my u, here is my v, and here is my w. Is there a way of combining v and u to get me to w? And by that, you're going to turn around and instantly say no, because v's too short and u's going in the opposite direction. I know, but again, think about how you can turn this around on its head. Can I scale v out anywhere? Well, hold on a moment. I'm already looking there. If I was to scale this out, and I'm actually going to draw a line here because it should turn in a line. If I do a line and make v bigger, just by multiplying it by some scalar, hold on a moment. Well, I've got this u vector here. Well, if I try and make that roughly parallel, and then will it let me move it? Oh, and it's actually joined it together. That's annoying. I didn't want it joined together. So let's undo that. All right, so if I have that v vector, can I move it? Can I slide it somewhere such that, well, sort of, yeah, because actually my my u vector might be something like that. But hold on, v is going that way and u is going that way. But if I was to reverse the direction of u, then actually life would be much, much better, because then actually I could scale v up, reverse the direction of u and scale it, and I could make it. And that's basically what linear dependence is. Can I take u and multiply it by some number, be it positive or negative, and v and multiply it by some number, and then get w in that way and there? Well, absolutely I can, and this is just me explaining a bit more. Remember, these notes can all be downloaded, and you can put them in your summary book and scribble all over. But if I can take 2 vectors or 3 vectors and scale them in some way, that it will, when I add those vectors together, give me a third vector in that set or another vector in that set, life is good. Now, This is just basically from the textbook, and I'm sorry that my head is basically all over it. I really should have reformatted these slides. Basically, this here is just telling you a little bit about what makes linear dependence. But all this says, in a very confusing way, is if I can take some vector w, and I can take other vectors v1, v2, and v3, and scale them by k1, k2, and k3, and when adding those together, I get w, they are linearly dependent. And conversely, if I can't do that, they are not linearly dependent. Right, so, and again, this is ridiculous. So I'm going to come back to this in a moment. The way we do this is if we go back to our column vectors, if I've got some column vectors, all right, if this is vector C and that's vector A and that's vector B, well, what I'm basically trying to say is this number here would have to be some multiplier of this number here and some multiplier of that number there, yeah? So if I put a plus sign in there and I say, oh, for example, M and N there, then what I now know is that C is equal to MA plus NB. Well, hold on, that's what they're saying there. So yes, to get vector C, can I do a scalar multiple of A plus a scalar multiple of B, and they can be different numbers or in fact the same, and get my answer. This to me here, again, it just seems a little bit stupid really, but anyway, if basically two things are equal, then what's on the left-hand side must be what's on the right-hand side. So that would suggest that M must be P and N must be Q. I've not yet read an example where that actually comes in useful. Right, here we go. How do we do this? Well, we use our calculator. Being able to use our calculator for a specialist maths exam is incredibly important. Yes, of the 20 questions on a multiple choice paper, about 17 or 18 of them are CAS enabled. You know how to use your CAS and all the functionality in there, you should be able to smash through those questions relatively quickly. Some of them are pencil and paper, don't get me wrong, and they will take time. But that is all down to exam technique. But here we go. I have three vectors, A, B, and C. Now, we got to make sure that none of the two vectors are parallel, and I'll come back to that in a slightly different video. If they are parallel, if there is a multiplier, if C, for example, was a multiplier of B, put them on opposite sides of the equal sign, right? But if they're not parallel, we can basically choose whatever. I always tend to use the last one. So if we write this in vector notation, I've got 5, 6, equals, we know we've got to have some sort of multiplier, M, times, let's say the first one, 2, 3, plus some sort of multiplier of 3 minus 1, n minus 1. Well, again, with vectors, we basically can multiply the top rows together and multiply the bottom, and we can turn them into equations. So that becomes 5 is equal to 2m plus 3n, and 6 is equal to 3m minus n. Well, all I've got here is a set of simultaneous equations. Well, once I've got a set of simultaneous equations, I'm not going to do it by hand. Why would you do that when your calculator can do it for you? Now, obviously, I've shown TI Inspired screenshots here. Sorry, guys, the school I'm currently teaching in is a TI school. In later videos, I actually have the ClassPad, I think, working on my computer, and I will try and alternate between the two. But generally speaking, the functionality is very, very similar. But basically, I've put this into my calculator. Now, because it has come out with a set of values, there is m and there is n. So it's telling me if I multiply each of those values in there by 23 on 5, and each of those values in there by minus 7 on 5, and then add the top values together, the bottom values together, I will get 5, 6. Or some multiple of that plus some multiple of this will give me this vector here. So, i.e., they are linearly dependent. We can do it in 3 dimensions. It doesn't actually matter, right? Again, if I look at this equation here, I can write it as 3, 4 minus 1 is equal to m lots of 2, 1, 3, plus n lots of minus 1, 0, and 1. I could do it that way. I think I've probably done it the other way around, so let's just actually reverse this. So I've got it, what is it, minus 1, 0, and 1. 3, 4 minus 1, and then 2, 1, 3. It shouldn't make any difference, guys. But again, what have I done there? Well, effectively, I've got minus 1 is equal to 3m plus 2n. So there we go, got minus 1 equals 3m plus 2n, yada yada. Put it into my calculator, solve for m and n, and what's come out? No solutions found. So in that situation, it is not possible to take a and b, some multiple of a and some multiple of b, and create that vector there. Ka-ching. Now be careful in exams, because every year they've generally asked for linearly dependent. Every now and again they throw in linear independence. Now, at the end of each video, I'm going to try and do some VCAA questions. What I suggest you do is pause the video and have a look and see what you think the answer is. This is what I'm doing to my group at the moment. So pause it if you wish to. Did you pause? Okay. So question 15 from the 2006 paper. I took that back from beginning, but you got the parallelogram shown where you are told the mod of A is equal to 2 times the mod of B. What does the mod mean? So the length of A is twice the length of B. So which of the following is true? Is A equal to B? Well, that would suggest that B was in exactly the same direction as A and twice as big. Well, B certainly is not in the same direction. It can't be that one there. So that can't be true. Put a line through it. A plus B equals C plus D. Well, again, if I was adding the lengths of those, possibly, but there are no modulus signs there. So is A plus B equals C plus D? Well, let's see what A plus B is. Well, A plus B would give me a vector going that way. What would C plus D give you? Oh, hold on a moment. It would have exactly the same magnitude, but it would be in the opposite direction. So again, and notice what I'm doing here. I'm thinking of this algebraically. I'm not banging stuff into a calculator. I'm not trying to do loads of geometrically. I'm not trying to do this algebraically. B minus D equals 0. B minus D equals 0. No, because if I actually was to swap D, that would be like adding B and that. If I add those together, that's not going to give me the 0 vector, but again, people got tricked on this. Hopefully, if you have already done this question, what you should notice is that A plus C. The correct answer is actually D, because if I take this vector here and add it to that vector there, I'm not changing the direction of C, so A plus C will actually put me back where I started from there. So again, these questions require you to think about it geometrically. The vectors A, B, and C will be linearly dependent when the value of lambda is. Now again, in this situation, what would we do? Well, we'd write it out in, and it wants it linearly dependent when lambda is. So I've got C, I plus K, they're missing a J term here. So that's 1, 0, 1. Would be equal to M times what I've got here, sum A, which is 1, 2, minus 1, plus N times lambda 3, 2. Interesting. How would we solve this here? Can your calculator solve this? Well, again, it wants to know, will it be linearly dependent when the value of lambda is? I suggest you put it into your calculator and see what happens when you solve that. You probably won't be able to use lambda there. Use a different letter like P, see what comes out. I know that my group, a lot of them did it by trial and error. They changed the value of lambda to 1, 2, 3, 4, and 5. And if I am correct, and obviously pause the video now if you don't want the answer, the correct answer was E, which was 5. That came from the 2020 paper. And finally, question number 12. Ooh, this is a tricky one. Again, pause it if you want to and have a go. Again, the trick here is necessarily true. Necessarily true means it has to be true for every single example, all right? Absolutely every single example. So if the mod of A plus B, so the length, I've got two vectors and add them together and find the length, is equal to the length of A plus the length of B, and A and B are not 0, which of the following is necessarily true? Right, okay. So the mod of A equals the mod of B. The length of A equals the length of B. All right, well, again, if we try and think about this geometrically, A might be going that way, B might be going that way. Well, what would A plus B be? Well, it would be this. So for every single example we could ever think of, that length plus that length always equal to that thing? No. So it can't be B, all right? So again, notice what I'm doing here, crossing off stuff. A equals minus B, all right? So the length of A equals minus the length of the minus of B. Is that necessarily true? Geometrically, can you draw that? Have a go. I'm going to tell you that is not true. Likewise, A is perpendicular to B. We've sort of already looked at that as well. So now let's look at A and C. The VCAA suggestion said that actually both A and C could actually be true, but only one of them is always true. Now, if we look at C, A equals B, that basically means we've got a vector A and a vector B. They are exactly the same length, and if I add them together, I am going to get the length of both of them, right? So if I take the individual length of that and the individual length of that and add them together, I'm going to get that. But what if B was longer? What if A was here and B was all the way there? Is that going to be true? Well, A is no longer equal to B. It was here in that one specific example, no longer here. So in which case C can't be right because it's only true for that one individual example. And in which case, what we do know then is that for the answer of A, we know here that so long as they are parallel, doesn't matter what length they are, then it will be necessarily true that that is them. Whoa! That was a long lesson. How long was it going for? 31 minutes. All right, they get shorter. I don't know, it was useful. Hopefully it was. I'm pretty much done for this particular video. There will be more videos hopefully coming in this series. Hopefully you will join me for those. Again, sign up to YouTube, follow me on mathsguru.com and TikTok, and let your mates and teachers know that this resource is there, and I'd be deeply grateful. If I don't see you again, please take care and stay safe.